Hi everyone, this is video number 9 of our complex number lecture. Okay. Currently on the screen is page 26 of P3 tutorial 10. Okay, so in this, from this page onwards, we will start to learn a new topic in the chapter, which is locus. Okay, so to fully understand locus for complex numbers, we will need the understanding of the contents of page 16. The geometrical interpretation of modulus and argument, eh, where v minus u is interpreted as the distance measured from u to v, and argument of v minus u is the angle measured from u to v. And such kind of understanding will be very important for us to understand locus fully. Okay. So let's go back to page 26. Okay, let's read through the first 2 points of the notes. Okay, so here we are learning locus of a variable complex number. Okay. The meaning of the word variable, it means not fixed. Variable means not fixed. Okay. So what do we mean by fixed and not fixed? Okay. For example, if I give you a complex number u to be 2 plus 3i, then its point representation on the Argand diagram. Here we have the Argand diagram. It will be the point 2, 3. Okay. So this point will be the point representation of the complex number u, and this point is a fixed point. Okay. We call this a fixed point because it has a fixed position and its position doesn't change. Okay. The coordinates must be 2, 3. Okay. So here when we talk about variable complex number, its point representation on the Argand diagram is not going to be a fixed point, but you can interpret it as a moving point, or some people like to interpret it as a collection of points. Okay, so a set of points means a collection of points. A collection of points. Okay. And here there can be infinitely many points. There can be infinitely many points. Such a collection, it may include infinitely many points on the Argand diagram, which satisfy a given condition. It can be illustrated using a graph where the set of points lie on the graph, or shaded regions where the set of points lie in the shaded region. Okay, so in this topic of locus, when we are asked to depict the locus of a complex number that satisfies a certain equation or inequality, our diagram can be a graph. For example, it can be a circle. So if the locus of the variable complex number z is a circle, then you can imagine z, the point representation of z as a moving point that moves along the circumference of the circle. Another way to interpret this diagram is that you imagine the circumference of the circle to be a collection of all points that satisfies some equation. We'll cover that in more detail later. Okay. And then when we have inequalities involving involving the variable complex number z, when we have inequalities, then it is possible to have a shaded region as the locus of the variable complex number. And we'll also cover that later. Okay. Okay, point number 2 says we will study 3 types of loci. Loci is just the plural form of the word locus. Okay. So we'll study 3 types of loci defined by complex equations and or inequalities. The variable points are usually denoted by z or w. So z or w are commonly used symbols in the topic of locus. And the z or the w will be the variable complex number that is described by the equation or the inequality. So in other words, we are looking for all points z or w, depending on which symbol they use, that satisfies the given condition. The given condition is usually in the form of an equation or inequality. So we are interested to know what is the collection of all points when it is depicted on an eigen diagram. And yeah, we want to find out all points that satisfies a certain equation or inequality. Okay. Okay, now let's look at the first type of locus. The first type of locus that we'll learn is circle. The second type is perpendicular bisector. Third type is half-line. We'll only learn three types of locus in our syllabus. Okay. We'll start with circle. A circle is, I think, the simplest one among the three. Okay. The locus of z expressed in the form z minus a equals r, where a is a fixed complex number and r is a real constant. Uh, wait, right. Okay, the locus of z expressed in the form of this equation, where a is a fixed complex number and r is a real positive constant, because they say r more than 0. It is a circle with center at the fixed point A, where the capital letter A is the point representation of the fixed complex number A. Okay, so it will be easier to understand if I give you some numerical examples first. Okay. Right. So for example, if I have z minus 1 plus 2i, it is equal to 3. Okay. So according to what the sentence above says, the locus of z, where z is the variable complex number, this z here is a variable complex number. So it's a circle with center at point 1, 2. Why is it 1, 2? Because 1, 2 is the point representation of the fixed complex number 1 plus 2i. This is a fixed complex number. And radius of 3 units. And where does the 3 come from? The 3 is this number on the right hand side of the equal sign. So, why is such an equation related to a circle? So first of all, let's recall what we have learned earlier on page 16. The geometrical interpretation of modulus, particularly table number 2 here. Right. Earlier we have learned that for the expression modulus of v minus u, it should be interpreted as distance measured from point u to point v, where capital U and capital V, they are respectively the point representation of the complex numbers small letter u and small letter v. So the way to remember this is that the complex number that comes after the minus sign, it becomes the starting point. It becomes the starting point. Where you measure the distance, and the complex number that comes before the minus sign is actually the ending point. It's the ending point. Okay. So going back to what we have here, if you treat 1 plus 2i as a complex number and z as another complex number, then the expression z minus 1 plus 2i, its geometrical interpretation is the distance measured from point 1, 2 to the point representation of z. Point representation of z. Okay. So for convenience, let me just call the point representation of Z as the point capital Z. Okay. So it's a distance from point 1, 2 to point capital Z. And so looking at the eigen diagram, what are the possible positions of your point capital Z? Okay, we know on an eigen diagram, okay, my point 1, 2 can be somewhere here. Okay. So as long as the distance from point 1, 2 to the point capital Z is 3 units, because in the equation that I give you on the left of your screen, we are setting the distance from 1, 2 to Z to be 3 units. And so as long as the distance from point 1, 2 to point Z is 3 units, then the equation is satisfied. So one point that would satisfy this equation is the point that is 3 units below 0.12, exactly 3 units below 0.12. Okay, so this will be one possible position of Z. Okay, but we also know that there are many other points that would also satisfy the equation. Okay, because I can also take a point 3 units to the right. 3 units to the right of 1, 2, and this would be another possible position of Z. Okay, I can also take 3 units up. This would be another possible position of Z. If I take 3 units to the left, this is another possible position of Z. But are these 4 the only 4 possible positions of Z? No, because there are actually infinitely many points that will satisfy the equation. In fact, if we construct a circle, with radius of 3 units, circle with radius 3, centered at the point 1, 2, then any point on the circumference can be a possible position of your point Z. Because the distance from this red colored Z to the point 1, 2 is guaranteed to be 3 units. Okay, if we take another point here, as long as this circle is a circle with radius 3 centered at point 1, 2, then this latest point Z here, it would also have 3 units away from the point 1, 2. And so in fact, Z can be anywhere. Z can be anywhere along the circumference. Okay. So in other words, the circle, the circumference of the circle becomes a collection of all points. It becomes a collection of all possible points Z that would satisfy the equation. And so this is the reason why the locus of Z is a circle, right, when you have an equation of this form. Okay, so let's go back to the notes at the top. Okay, so the note says whenever you have an equation of this form, as long as you have Z minus some fixed complex number equals to a positive real value, what you need in this bracket here is just a fixed complex number. Okay, then the locus of Z that satisfies this equation, it will be a circle with center at the point representation of this fixed complex number and having a radius which is the same as the positive real value on the right hand side of the equation. Okay, so this is the way we remember it. Okay, as long as you have modulus of Z minus A equals to R, okay, then the locus will be a circle. Now, in our syllabus, not only we need to know how to draw the locus, we also need to know how to describe in words. And so the description in words will be this part highlighted in pink. Okay. Circle with center at the fixed point, then you state the coordinate of the point, and radius, you state the value of the radius. Okay, just like what I state here in red color. Okay. Circle with center 1, 2, and radius 3. Okay, this will be a description in words for the locus. We also need to know how to describe the locus in words according to our syllabus requirement. Right. Now let's move to the next part of the notes, point number 2. Remember to label the diagram with the axis, the origin, and other important features of the locus, which include center of the circle, its radius, and the axial intercepts if they can be easily found. Okay, so when we are asked to draw the locus in the form of a circle on the Argand diagram, there are several information that we are expected to display in our diagram. So, of course, the basic one is label the axis as REZ and IMZ, and label the origin. And these are the basic things when drawing any Argand diagram. And any other important features of the locus, it must be labeled clearly, which include the center of the circle. And so, if your center of the circle has coordinates of, let's say, 2, 3 here, then make sure you align some dotted lines there so that the coordinate of the radius, it can be easily read by the examiner. Radius, um, it would be good to uh, draw out a radius like this green colored arrow here. So just draw a radius from the center towards any point on the circumference, and then you label your radius as R. I mean, you label the numerical value for the radius. And so if this is a radius of 1 unit, then you would label the number 1 here, and to make it clear to your reader that this is a circle with radius of 1 unit. Uh, Alternatively, if it is very clear from your diagram that your circle has a radius of 1, then it's actually acceptable not to label. So what I mean here is, if it is very clear from your diagram that this point is 1 unit to the left of the center of the circle, and this point is 1 unit to the right of the center, and this point is 1 unit below, and the point above is exactly 1 unit above by the coordinates. If it's very clear, then it is acceptable not to label the green colored radius of 1 unit. Right? So yeah, just make sure that in your diagram, your examiner can easily identify what the radius is. Axial intercepts. So axial intercepts means the x-intercept and y-intercept. So if x-intercept and y-intercept can be easily found, and then they expect you to display the intercepts on your diagram accurately. And so if your circle, for example, if your circle would pass through the origin, if your circle would pass through the origin, then in your diagram, it must be displayed as such. Or if your circle passes through the y-axis at a y coordinate of 2, for example, then it should be displayed accurately on your diagram. Okay. However, if the axial intercepts cannot be easily found, in the sense that it would require tedious calculations to obtain the x or y intercepts, then they wouldn't expect you to label on your diagram. And so later when we do some exercise questions, you will know what I mean by can be easily found. Okay. Okay, now let's move to point number 3, regions as loci. Okay, so when you have inequalities instead of equation, then it is possible to have a certain shaded region as the representation of your locus. Okay. So let's read through point number 3 here. The first bullet point says, when you have the equation modulus z minus a equals to r, okay, the locus of it is the circumference of a circle with center a and radius r. And we have covered this just now. Okay. If you have modulus z minus a strictly less than r, then the locus of it is all points within a circle with center a and radius r. So it will be the same circle as the equation in the first bullet point. But now it is the inside of the circle or the interior of the circle that should be considered as the locus of Z that satisfies the inequality. Now, why is it this way? Okay. Recall that Z minus A with a modulus, it means the distance from point A to the point representation of Z. Okay. So if you have a circle centered at A with a radius of R, and then this inequality says the distance from A to Z must be strictly less than R. We know if we take a point on the circumference, then the distance from A to that green colored point, it must be exactly R. If you take anything shorter than that, which means if you take your point to be in the interior of the circle, if you take your point to be the interior of the circle, for example, somewhere here, then this distance must be less than R. It must be strictly less than R. Another example, if I take a point somewhere here in the interior of the circle, because I know this distance must be R, then this distance must be less than R. So, in fact, as long as I take a point, any point, in the interior of the circle, and I measure the distance from A to my purple colored point, as long as the purple colored point is in the interior of the circle, the distance must be strictly less than R. Okay. That also means when we draw the locus, to indicate that we only want to include the interior of the circle, but not the circumference of the circle, we have to draw the circumference in dotted lines. And so if you're asked to draw a locus of Z where modulus Z minus A is less than R, and then the way to draw it out is you would draw the circle using dotted lines. You would draw the circumference of the circle using dotted lines to indicate that the circumference is not included. Then you would shade the interior of the circle. You would shade the interior of the circle. Okay. Remember to draw your circumference using dotted lines. If you draw your circumference in solid line, it will be wrong. Okay, because when the inequality is strictly less than R, it is an important thing to show that the circumference is not included. Okay, so you must display that the circumference is not included by drawing the circumference using dotted lines. Okay. Yeah, and this is what I mentioned in the sentence here. Okay. So you will shade all the points within a circle. Okay. In other words, shade the interior. Okay, but the circumference, please draw using dotted line. And then the examiner will know that the circumference is not included. Okay. In questions where there's only one locus to draw, then it's okay not to label this as locus of Z. I mean, it will be good if you just point an arrow into the shaded region and say this is locus of Z, but it's also okay not to label these few words locus of Z here. Okay. Only for questions where you are asked to draw two different locus on the same diagram, then it becomes crucially important to label which graph belongs to which locus. Okay. Yeah, and going back to the diagram earlier for a while. Okay, so for the case when the locus of Z is the circumference of the circle, then you can also choose to label this as locus of Z. You can just label it this way. You just point an arrow. Yeah, just point an arrow on the circumference and say this is locus of Z. Then it will be understood. If you do not label, it is actually fine. Only for the case when you need to draw two different locus on the same diagram, then it becomes crucially important to label. Now, going to the third bullet point, if your modulus z minus a is less than or equals to r, again, modulus z minus a means distance measured from point A to point Z. At this time, we allow the distance from A to Z to be strictly less than r and also be equal to r. So in other words, we allow the circumference to be included this time. So when you draw the graph for the locus of z minus a less than or equals to r, then your diagram will look like this. The circumference will be drawn using a solid line centered at A and label the radius as r. In fact, for the previous diagram just now on the right of your screen, we should also label the radius. Okay, and then now you would shade again the interior of the circle. And so when the circumference is drawn using solid line, it's understood that the circumference is included as part of your shaded region. Okay. And you can just label here locus of z. If you don't label locus of z, it's actually fine. If the question only asks for one locus, then it's actually fine not to label. Okay. The question in the rectangle box down there, how can we illustrate the locus of z defined by modulus z minus a is strictly more than r? Okay. So again, modulus z minus a means distance from a to z, the distance from a to z. And so if you have a circle centered at a with radius r, if we have a circle like this, then as long as we take a point at the outside of the circle, this distance from A to the green point, it is definitely more than r. As long as you take any point outside of the circle, at that point, when you measure the distance from A to the green point, the distance must be more than r. Okay. So if they ask for modulus z minus a strictly more than r, then we don't allow the circumference to be included. And so in such a case, we will have to draw our circumference using dotted lines. And then we would shade now the exterior of the circle. We will then shade the exterior of the circle, and this region, this shaded region, it will be extended indefinitely to all directions. So it's only the circumference and the interior of the circle that is not shaded. Everything outside would be included in your shaded region. So your shaded region here would have an infinite area, because you can extend the shaded region to the far left, far right, far above, and far below. Okay. But for the case when they allow r to be included as the distance, then here you would draw the circumference using solid lines. Okay, so if I draw the circumference using solid lines, then it would be the locus of modulus z minus a more than or equals to r. Okay, because now they allow the distance from a to z to be exactly equal to r. Therefore, circumference is allowed to be included. Yep. So a quick summary here. If you have mod of z minus a equals to r, then your locus of z, it will be just the circumference of the circle. It will be just the circumference of the circle, centered at point A with radius r, and here is your locus of z. Okay. If you have z minus a strictly less than r, then it will be the interior of the circle, not including the circumference, because we don't allow the distance to be exactly equals to r. It will be the interior of the circle. And to show that the circumference is not included, we must draw the circumference using dotted line, and then we will shade the interior. We will shade the interior, and the interior or the purple region is the locus of z. If you have z minus a modulus less than or equals to r, Then it will be the interior of the circle, but this time we include the circumference. Centered at A with radius R, circumference is included. So we draw the circumference using solid lines. Okay. The purple colored region is the locus of Z. Okay. When circumference is drawn using solid line, it is understood that the circumference is part of your shaded region. Then if you have modulus Z minus A strictly more than R, then it will be the outside of the circle that you should shade. It is outside of the circle. Circle centered at A with radius R. But this time I need dotted line. I need dotted line for my circle. Because I don't allow the distance from A to Z to be exactly R. So circumference cannot be included. And I have to shade the exterior. Shade the exterior. So everything outside the circle will be included. So this is locus of Z. And of course, you can extend your shaded region indefinitely towards all directions at the outside. And lastly, if you have modulus Z minus A more than or equals to R, then it is also the exterior of the circle. But this time we allow the circumference to be included. We include the circumference, so we draw using solid line, center at A, radius R, and I would shade again the exterior. Okay, so that whenever a point in the shaded region is taken, the distance measured from A to Z, it will be more than or equals to R unit. So this is the whole idea of locus. Okay, now let's move to page number 27. Okay, perpendicular bisector. Okay, so here we have another different form of equation that we will have to remember. Okay, so just now for circle, it is of the form modulus Z minus A equals R. And now for perpendicular bisector, it is again so for perpendicular bisector, you have a different form of equation. It is having two modulus on both sides of the equation. Okay, so you have modulus Z minus A on one side, modulus Z minus B on the other side. So first, let's interpret the geometrical meaning of each expression on each side of the equation. Okay. If point capital A and capital B are the point representation of the fixed complex numbers A and B, this is a fixed complex number. This is fixed complex number. B is another fixed complex number. Right, so if capital A and capital B are the point representations of A and B respectively, then the left-hand side, the meaning would be distance measured from point A to point Z. But of course here your Z is a variable point. The position of your Z can be changing. Then on the right-hand side, the meaning of it is the distance measured from B to Z. Distance from A to Z is equal to distance from B to Z. Okay, so this is what the equation means geometrically. Now, A and B are two fixed points on the Argand diagram. Okay, so let's just imagine that in a two-dimensional plane, or in the Argand diagram, A and B are just two fixed points. Okay, so where can we place the point Z such that Z is equidistant from A and B? The first point that comes to mind to most people, it will be the midpoint of A and B. It will be the midpoint of A and B. Right, so if I take the midpoint of A and B, let's call it M here. If M is the midpoint of A and B, then M will be equidistant from A and B. Distance from A to M and distance from B to M would be equal. So in other words, M becomes a possible position of Z. So let's just call this point Z here. So it is one possible position of point Z. But this is not the only possibility, because if I draw a perpendicular line to AB, a line which is perpendicular to AB and passes through the midpoint of AB, in other words, perpendicular bisector. Right? So if this is perpendicular bisector of AB, making a 90 degrees here, and then every point along the perpendicular bisector is also equidistant from points A and B. Now, why is it so? Okay, now to convince you that any point along the black line would be equidistant from A and B, let me just illustrate it by choosing some random point here. Let's suppose that this point, let's call it point A. No, I shouldn't use A. Let's call it point X. Okay. Now, I claim that distance XA is equal to distance XB. So how can I convince you? Okay. Okay, let me complete this right angle triangle. Okay, so you can see there are two right angle triangles here. Okay, let me just call the midpoint of AB to be M. Let's call this to be M for now, so that you can see things clearly. But AMX is a right angle triangle. BMX is another right angle triangle. Okay, I know AM and MB are the same. Okay, so let's call this distance D1. Okay, if AM has distance D1, MB also would have distance D1 for sure. Okay, because they are we have equal distances for AM and MB because M is the midpoint of AB. Okay. Now let's call the distance MX. Okay, let's call the distance MX to be, let's say, D2. Okay, so here I'm letting D1 equals to AM equals to MB. Okay, I let D2 equals to the distance MX. Okay, then what is the distance AX? The distance AX by Pythagoras, looking at the right angle triangle AMX, the distance AX is a hypotenuse in that right angle triangle. And I know it is a square root of D1 squared plus D2 squared. And similarly, if I look at this right angle triangle on the right, and I want to find the distance BX. So BX is the hypotenuse line, which by Pythagoras I know is again D1 squared plus D2 squared with a square root. And notice that these two are exactly the same thing, which means AX must be equal to BX, and my claim has been verified. My claim has been verified. So it is a correct claim. Okay, so by similar reasoning, you can prove that, you can again verify that this point, let's call it Y, AY and YB must also have equal distance. If I take this point, let's call it G on the other side, AG and GB, it must also have equal distances. And so if I call this H, AH and HB must also have equal distances. So you can prove it using the same reasoning. Okay. All right, so this means for any point along my black line, in fact, I can extend my black line indefinitely. I can extend my black line indefinitely. Any point along my black line, it will be equidistant from point A to point B. We can easily prove it using the same reasoning. Okay. So this explains why the equation modulus z minus a equals to modulus z minus b, the possible positions of z, it will be anywhere along the black line. It will be anywhere along the black line. Okay, because this equation itself, the geometrical meaning is distance from A to Z is equal to distance from B to Z. Okay, and this equation or the condition will be satisfied as long as Z is a point along the black line. Okay, and what is a black line? Your black line is the perpendicular bisector of AB. Yeah, so this is so I hope now you can accept why you should get a perpendicular bisector whenever you have an equation of this form. Okay. So the description of the locus in words, it is perpendicular bisector of the line segment connecting the fixed point A and B. So this is the description that you have to know how to write in words. Okay. Okay, and of course here A and B are respectively the points representing the fixed complex numbers A and B in the Argand diagram. Okay, as you can see here as printed for you. Okay, so when you draw, okay, I'll just give you one example. Sketch the locus of Z, which satisfy or where modulus of Z minus 1 plus 2i is equal to modulus of Z minus let's say 3 plus 4i. Okay. So the description, usually we don't need to write the description of the locus unless the question asks for a description. Okay. So the locus of Z is the perpendicular bisector of the line segment joining the fixed point or joining the points 1, 2, and 3, 4. Because your 1, 2, and 3, 4, they are the points A and B respectively. 1, 2 is a point representation of 1 plus 2i. 3, 4 is a point representation of 3 plus 4i. So how would the Argand diagram look like? In this chapter, in this topic of locus, it is important to draw everything to scale. I mean, you have to be 100% accurate when drawing locus. Only for locus. In other chapters, usually when we sketch graph, I said you don't have to be 100% accurate, but only for locus of complex number, we have to be 100% accurate, which means you must measure using ruler. Like 1 cm to be 1 unit, or maybe 2 cm to be 1 unit, depending on how big is the space you have there. IMZ, REZ. So first, when you draw your perpendicular bisector, you first find, you first plot out the point 1, 2. And so use dotted line to align your the position of 1, 2 so that the examiner can easily read. And 3, 4 would be here. 3, 4 would be here. Use a dotted line to connect the 2 points. If this is 1, 2, this is 3, 4. Use a dotted line to connect. Now, to make sure that the diagram that you draw looks nice and accurate, it is good to know how many units horizontally and vertically does your slanted line here cover? Okay, so your slanted line here covers 2 units horizontal, 2 units vertical. Okay, so it kind of forms a square here. It kind of forms a square here. So your perpendicular bisector, it will look like this. It will look like this, and if you continue on, and if your diagram is accurate enough, it would intersect the x-axis at 5, and it will intersect the y-axis also at 5. Right, so this red line, it would be your locus of Z. And label the equal distance symbol. Okay, so here are the few important things to display when drawing perpendicular bisector. Okay, first thing, the 2 points, 1, 2, and 3, 4. Make sure they can be easily read from your diagram. So it will be good to plot crosses or just blacken the dot there, so that people will know these are the 2 points where you would draw a perpendicular bisector for the line segment. Okay. Then next thing to display is the 90-degree and also the equal distance symbol, okay, so that people will know that you are trying to draw a perpendicular bisector. And another thing is, if the x and y intercepts can be easily found, in this case, they can be easily found. As long as you draw your diagram accurately, you should be able to intersect the x-axis at 5 and the y-axis at 5. So these are also things that examiner will look for. Whether or not you label the words locus of Z is not so important here, because there's only one locus that we are drawing. Okay. Okay, later on page 29, we'll do more practice on drawing locus. Okay, so on page 27, this is just an introduction. Okay, later we'll do more practice on this. Okay. Okay, now let's move to the next point in the note. Yeah, so on your diagram, this is a reminder. Remember to indicate that the two lines are at right angles to each other, which means label the 90-degree symbol. And the perpendicular bisector is equidistant from A and B, which means label the equal distance symbol at these two short lines there. Okay, next. Okay, so similar to the case for circle, where when we have inequality, we will have some shaded region as a locus. Okay, so here is a similar idea. Okay, when you have inequality instead of equal sign in the middle, then the locus becomes a shaded region. It is not only a straight line. Okay, so let's read through the notes here. Okay, let Pxy be the moving point or variable point that represents z equals x plus yi on the eigen diagram. So they are just letting p, they say let p be the point representation, be the point representation of the complex number z. And this is a variable complex number z. Okay. And the first bullet point says when z minus a, the modulus of it is equal to modulus of z minus b, the point Pxy moves so that it is always the same distance from A as it is from B. The locus is therefore the perpendicular bisector of the line segment AB. Okay, so this is just a repetition of what I explained earlier. Okay. Modulus z minus A equals modulus z minus B. The geometrical meaning means distance from A to Z. Here they are just letting P be the point representation of Z. So distance from A to P is equals to distance from B to P. And so P can be just anywhere along the perpendicular bisector of AB. And so if this is A, this is B, you just need to draw a perpendicular bisector. Perpendicular bisector of AB, and then your P, you can imagine it as a moving point along the perpendicular bisector. And so P can be anywhere. And so locus is a variable point. Some people interpret it as a moving point. Some people interpret the line as a collection of all possible positions of P. Yeah. Right, so if you imagine it as a moving point, then you can say that P is a point that moves along the black line. Okay, point 2, the second bullet point says, when you have inequality, modulus of Z minus A is less than modulus of Z minus B. Now if I change my equal sign to less than, then here it also changes accordingly. The distance from A to P is strictly less than distance from B to P. Okay, so what would change on the diagram? Okay, now where can be my possible positions of P? Okay, I will still draw the perpendicular bisector. At this time I'll draw it using dotted line. Okay, now we know that if I take a point, let's call it point G here. Okay, so G will be equidistant to A and B. Okay, but if I want the distance from A to B, from A to P to be shorter than distance from B to P, this one I want it to be shorter. This one I want it to be longer. So, of course, we have to take a point that is on the left of G. Okay? In other words, the point on the left of the perpendicular bisector. Okay? We have to take this as a possible position of P. Okay? So, and if you really measure the distance from P to A and from P to B, P to A will be shorter. P to B will be longer. Okay? So, this point P would satisfy the inequality, okay, where the distance AP is shorter than distance BP. Okay, in fact, as long as you take any point on the left of the perpendicular bisector, let's call this P1. Okay, so P1 is slightly to the left, and P1 is slightly to the left of the perpendicular bisector. Okay, then the distance from A to P1 will be slightly shorter than the distance from B to P1. Okay, this is a guarantee. Because we know if we want distances to be equal, and then we just take any point on the perpendicular bisector. And so since P1 is slightly to the left of the perpendicular bisector, and then AP1 must be slightly shorter than BP1. Yeah, so if I take this point P2 here, it is also a possible position of P. And if I take point A itself, if I take point A itself, what is the distance from A to A? It's 0. Distance from B to A is of course longer than 0. And so it would still be a possible position of P. Point A itself is still a possible position of P because in this case, AP having a 0 length, it is of course shorter than the distance BP. And of course, if you take a point to the left of A, then of course PA must be shorter than PB. If I take any point here, any point here, any point here, and then of course these are all possible positions of P where PA is shorter than PB. Okay, so in other words, the shaded region will look like this. Okay, the shaded region will look like this. If this is point A, this is point B, we would still draw the perpendicular bisector. Because here is a strict inequality. This is a strict inequality. We don't allow distances to be equal. That's why the perpendicular bisector itself cannot be included. And so we have to draw the perpendicular bisector using dotted lines. And then we will shade the region on the left of the perpendicular bisector. Okay. So how do we remember this? Okay. You should not remember whether you should shade the left or the right. What you should remember is if you want the distance from A to P to be shorter than the distance from B to P, then you should shade the side that contains A. If you want distance from A to P to be shorter, then you should shade the side that contains A. And so this is the easy way to remember. Okay, so going back to the numerical example that we had earlier. Okay, so in this diagram, if I change the question to become an inequality, if I change it to be strictly lesser than, and then I should shade the side that contains 1 plus 2i. In other words, I should shade the side that contains 1, 2. Should shade this way. And my red line should be converted to become dotted lines. My red line should be converted to become dotted lines if this is a strict inequality. Yeah, so it should become something like this. Okay, so easy way to remember is the shorter side. If 1 plus 2i is on the shorter distance side of the inequality, then you would shade the region that contains the point 1 plus 2i. And then you can always check whether it makes sense or not. Like if you take a random point in your shaded region, for example, I take the point of 0, 3 here. Okay, so if you measure the distance from 1, 2 to 0, 3, compared with the distance from 3, 4 to 0, 3, this distance is shorter. Okay, and therefore satisfies the inequality. Okay, because the inequality says distance from 1, 2 to z must be shorter than distance from 3, 4 to z. Okay, so any point in our shaded region here, it will be a possible position of the point z. And of course here, the locus of z would then be the shaded region. Okay. Yeah, so I've covered the second bullet point here. So it says when you have a strict inequality, um, they say the point P or the point representation of Z, it must be nearer to A than to B, because the distance from A to P must be shorter than distance from B to P. And the perpendicular bisector would mark the boundary of this region, but it's not included. Therefore, we draw it using dotted lines. Therefore, we draw using dotted lines. Okay. Then, what about the third bullet point here? Right, so if we have already learned the second bullet point, and the third one will be just a slight modification. Okay, so if you have modulus of z minus a less than or equals the modulus z minus b, the only difference between the third and the second bullet point is that now we allow the distances to be equal. which means the perpendicular bisector itself can now be included. Okay, so for the case of z minus a less than equals z minus b with modulus, so if this is point A, this is point B, and I draw my perpendicular bisector. Okay, this time I can draw it using solid line. Okay, perpendicular bisector can be drawn using solid line, and because I need this distance to be shorter, distance from A to Z, I need it to be shorter than distance from B to Z, so I should shade the region that contains A. To shade the side that contains A. So it is this side that should be shaded. And this time, the boundary or the perpendicular bisector itself can be included, therefore drawn using solid line. Because we allow the distance from AZ, we allow the distance AZ and BZ to be equal. So this point can be one possible position of Z. This point can also be another possible position of Z. Okay, next is half line. Okay, maybe before I go to half line, just a very quick summary for perpendicular bisector. Okay, so for perpendicular bisector, we have to identify it as, the form of the equation of inequality that we should identify is that you have a modulus on each side. Right? So if you have modulus z minus a is equals to modulus z minus b, okay, then what you have as your locus is the perpendicular bisector of AB. If you have modulus z minus a is less than modulus z minus b, then it is the perpendicular bisector. You will still draw the perpendicular bisector of AB, but because it's a strict inequality, the perpendicular bisector itself should not be included. So we would draw perpendicular bisector using dotted lines, and then we would shade the region that contains A, because the fixed complex number A, it occurs at the shorter distance side, where your distance AZ has to be shorter than distance BZ. So we would shade the region that contains point A. And you can always check that if you take a random point in your shaded region here, the distance AZ is shorter than distance BZ, so it is correct. Right. And this time our locus will be the shaded region here, locus of Z. Okay. Next, modulus Z minus A less than or equals to modulus Z minus B. We would still draw perpendicular bisector of A and B, but this time we allow the distances AZ and BZ to be equal. Okay, so perpendicular bisector can be drawn using solid line, and we would shade the region that contains A, because A occurs at the shorter distance side of the inequality. So we shade this region. The locus of that will be this shaded region, including the perpendicular bisector itself, right? Because the perpendicular bisector is drawn using solid lines. Okay, now let's move to the third type of locus, which is known as a half line. Okay, now what do we mean by half line? Okay. Okay. When we mention the word line, a line is a straight line that can be extended indefinitely. It can be extended indefinitely in at both ends. At both ends. So for example, when we say this is the graph of y equals x plus 1, this is a line, y equals x plus 1, and then this line can actually be extended at both ends. Okay. So here, when we call it a half line, okay, a half line can only be extended indefinitely at one end. It can only be extended indefinitely at one end. Okay, so this is the difference between half line and line. Okay. Line can be extended at both ends. Half lines can only be extended at one end. So this is the major difference and why we are using a different term to call this half line. So if you refer to this printed diagram down here, it can only be extended on one side. You can extend this way. Okay, but you cannot extend on the other side. This side you cannot extend. We cannot extend. That's why they call it a half line. They don't call it a line. Okay. So what is the equation for locus in the form of half line? It will involve the argument expression. So let's go back to page 16. Okay, on page 16, we have covered um, geometrical interpretation of argument. Okay. Okay, so we'll look at this expression here and what is the geometrical interpretation. So argument of v minus u, just like before, u would become the starting point, v becomes the ending point, and argument has something to do with angle. So argument v minus u is the angle measured from u to v. Okay. This is an informal description, angle measured from u to v, because at point u, we are going to draw, at point u, if this is point u, this is point v. At point u, we are going to draw uh, a horizontal line towards the right. It will form a vector connecting u to v, and we'll measure this angle here. So this angle here, it will be argument of v minus u. Okay. And so this is what I mean by angle measured from u to v. And this description is very informal, but it's like a convenient way to describe it using a short phrase. Okay. So argument of z minus a, where a is a fixed complex number. If capital A is the point representation of the fixed complex number a, then argument of z minus a, it means the angle measured from a to z. The angle measured from a to z. Okay. So if angle measured from a to z is theta, for example, I give you this argument z minus 1 plus 2i is equals to pi over 3. Okay, so this means angle measured from 1 to z is equal to pi over 3. Okay, so if you look at it diagrammatically, if this is point 1, 2, from the point 1, 2, I draw a horizontal line towards the right, and from this horizontal line, I measure an angle of pi over 3 in the positive direction or anti-clockwise. Then I draw a line here. If I take anywhere along the line, if I take any point along the green solid line, then I notice that if I take this as Z, then angle measured from 1, 2 to Z using the usual way. The usual way would be I would draw a horizontal line starting from 1, 2. I connect a vector from 1, 2 to Z, and then I measure the angle. It will give me pi over 3. So if I take Z to be further away, as long as it's still along the green line, it still works. Okay? So right now, if I measure angle from 1, 2 to Z, I would still draw a horizontal line starting from 1, 2. I will connect a vector from 1, 2 to Z, and then I measure uh, the angle from the horizontal direction towards the vector. It is still pi over 3. You can take another further point along the green line, and you can check again. The angle obtained from 1, 2 to Z would still be pi over 3. Okay, one thing to notice is that the point 1, 2 itself should be excluded from the locus of Z. The point 1, 2 should be excluded because what if Z happened to be at 1, 2? What is the angle measured from 1, 2 to 1, 2? Angle from 1, 2 to 1, 2 cannot be measured, it's undefined. Angle from a point to itself is undefined because there's no vector you can form from a point to itself. That is a zero vector. So you can't really draw an arrow directed from a point to itself. And because of that, you can't figure out the direction of the vector. Since this vector has no direction, there's no way to measure any angle from the horizontal direction to the vector. So this would be undefined. And if you convert this into algebraic form, angle from 1, 2 to 1, 2, we know that if I take argument of a complex number minus another complex number, it gives me angle from a point to another point. Right? So this starting point of 1, 2, I should fill in the corresponding complex number here at the back of the negative. The ending point should be at the front. When both of these yellow and blue points are 1 plus 2i, it becomes argument of 0. And earlier in this chapter, we have learned that argument of 0 is undefined. It's undefined. Okay, so this explains why the starting point should be excluded. Now, if we look at this equation, if 1, 2 is a possible position of point Z, that means 1 plus 2i will be a possible value that the small letter z can take. Okay, but once you sub in 1 plus 2i here, the left-hand side of the equation will be argument of 0, which would then become undefined. Okay, when the left-hand side is undefined, it can't be equal to pi over 3. Okay, so that's why 1 plus 2i is not a possible value of z that satisfies the equation. And therefore, the point 1, 2 should be excluded from the locus of z. Right? So z cannot be here. Right? Z cannot be here. Right? And usually to indicate that the starting point of the half line should not be included, right? We will draw the starting point using an empty circle or an empty dot. Okay, so the printed diagram is how people would usually draw the locus for a half line. So they will draw the starting point of the half line using an empty dot. And then they will draw a straight line at some angle measured from the horizontal direction to the right. And that's it. That is the locus of that. Okay, so when you draw your half line, the thing to take note of first is this empty dot at the starting point. Next, draw a dotted line as the horizontal direction towards the right, and then label your angle. Label your angle. Okay, so if your angle is pi over 3, you will label pi over 3 here. Okay, then what about the description? Okay, the description is half line starting from the fixed point A, excluding the point A itself in brackets, which means in your description it's okay not to write the phrase in bracket. You just need to know that the point A itself should be excluded. That makes an angle of theta anti-clockwise with the positive direction of the real axis. Okay, so in a formal description, when the question asks us to describe, we will avoid using the phrase x direction, but rather we will prefer to use the phrase positive direction of the real axis to bring out the meaning of positive x direction. Because in an Argand diagram, the x-axis has been renamed to become the real axis, and so we just follow the new name. And there's a note down here. It says when theta is negative, then the underlined words in the description, the phrase underlined in black, are to be modified accordingly, because if theta is negative, then the angle is actually clockwise. It's not anti-clockwise. I just gave you one example. If you have argument of z minus 2 minus 4i is equals to negative 2 pi over 3. And then the description would be, you would say locus of z is a half line starting from the point. So the starting point will be the complex number that comes after the minus. So it's the point 2, negative 4. That makes an angle of 2 pi over 3 radians. And whether or not you state the radian is not important. If you don't mention radian, it's understood to be in radians. So that's so it makes an angle of 2 pi over 3 radian clockwise. Okay, so the clockwise already brings up the meaning of negative angle. When I mention angle clockwise, it is a negative angle. With the positive direction of the real axis. Yeah, so this will be a formal description if you're asked to describe a half line. And so the keywords are half line, and then start from which point, then it makes an angle of 2 pi over 3, and that angle in what direction? Okay, so 2 pi over 3 clockwise is a keyword here. Okay, so okay, let me start again. First keyword, half line. Second keyword, start from the point 2 minus 4. Third keyword, angle 2 pi over 3 radian clockwise. And fourth keyword, that angle is with respect to the positive direction of the real axis. Okay, so 4 keywords overall. Half line, start from which point, what angle in what direction, and that angle measure starting from where. Let's go back to the notes, page 28. Can I explain why the point A itself must be excluded? This one I've already explained it just now. It's because it's because argument of 0 is undefined. If the complex number represented by point A is substituted into z in the equation, and then the argument expression would become argument 0, which then becomes undefined. Yeah, so that's the reason why the starting point of the half line is always excluded. Let me just draw out the half line represented by this equation. Okay. So this would be imaginary axis. 2 minus 4 is in quadrant 4. Okay, so I allocate more space for quadrant 4 here. Okay, so just now I mentioned that in the chapter of locus, you must draw to scale, and not only that, you must use the same scale for your x and y axis. And so if you're using 1 cm for 1 unit for your x axis, then you must be using the same scale for your y axis as well, so that your diagram doesn't become distorted. -1, -2, -3, -4. Okay, 2 minus 4. Okay, so this is an empty dot. Okay, the equation that I have here is argument of z minus 2 minus 4i is equals to minus 2 pi over 3. Okay, so from this direction to the right, I need to measure an angle clockwise by 2 pi over 3 radians. Okay, 2 pi over 3 is 120 degrees. Okay, 2 pi over 3 is 120 degrees. So it doesn't need to be 100% accurate because you are not expected to bring a protractor during the exam. But at least you should know that 120 degrees is more than 90, less than 180, and also less than 135. Now it's important to know where is the so-called 45-degree direction. A 45-degree direction, it will be this direction here, where it leaves at 45 degrees here. So what's so special about 45-degree direction? A 45-degree direction, the horizontal distance and vertical distance covered by the slanted line will have the same magnitude. So yeah, so when I say the phrase 45-degree direction, it can be a line with gradient +1 or -1. So for example, this line, which makes a 45-degree to the horizontal, I also call it a 45-degree line. This is just my informal way of calling it. And the more technical way of calling it is, of course, this is a line with gradient -1, and this is a line with gradient 1. Gradient 1. Yeah, so whether you have a gradient -1 or gradient 1, as long as the slanted line makes a 45-degree to the horizontal, you should know that such a 45-degree line, it will cover the same distance horizontally and vertically. Yeah, anyway, let me just erase all the messy things here. Okay, so what I need to draw here is a 120 degrees. So I need to know that 120 degrees is less than 135. Like if this is my 45-degree line, then this angle would be 135. But 120 is slightly less than 135, but more than 90. So I know that my y-intercept, it should go below -6. It should go below -6. It should go this way. And since to obtain the exact coordinate, the exact y-intercept would be quite tedious. It will involve some computation. Our syllabus or our mark scheme, usually they won't expect us to find when it is not very straightforward to find. Okay, so this value here, you don't really need to find. Okay, the y-intercept, you don't really need to find it because it would be quite tedious. So what you need to do is just to label this as your 2 pi over 3 radians. I will just label the magnitude here as 2 pi over 3. Since this angle is measured in a clockwise direction, then it indicates a negative angle of 2 pi over 3 for the argument. Right. Yeah, so my black line would be the locus of Z. And yeah, that's all that you need to draw for half line. During the exam, of course, when a line is supposed to be a straight line, you should draw it using ruler. Your axis should be drawn in ruler. Uh, your dotted lines here should also be drawn using ruler. And of course, your half line in black color, which is supposed to be a straight line, should also be drawn using ruler. Okay, I'll end this video here. In the next video, I will discuss the questions on page 29.